Okay, let me go over the calendar real quick here, just to show you what's coming up. We did particle motion yesterday. If we have time, we will do some more practice with that additional worksheet that you picked up yesterday. Linear approximation is our topic for today. Linear approximation, really, we're just, all this really is you get your tangent line equation and then you plug in whatever decimal they give you. So we'll just practice with that. But really the big topic that we really want to make sure is the focus here is related rates. So we'll start related rates on Monday. We'll spend 2 days on that. We may even bleed into Wednesday because indeterminate form, L'Hopital's rule, that's really easy and quick, so we can spend more time with related rates. We'll have a quiz review on Thursday, but maybe we can even start quiz review on Wednesday. Friday, we're going to start our next unit, but this won't take long. Maybe we can build in a little bit more quiz review, and then your quiz 4.1 to 4.4 will be on not this Monday, but the coming up Monday. So really the big topics are PVA and related rates, but really it's related rates that's the focus here. And then these smaller topics, linear approximation, L'Hopital's rule, those are quick and easy, but the focus is really related rates. Okay, and then unit 5. And I think this is going to be our final unit before we go into antiderivative. So pretty much by the time we get to the end of this month, we would have covered, for the most part, all the AB first semester topics. Okay, so we're moving into the AB second semester topics in October. Okay. Okay. There is going to be homework due on Monday, so I'll make a reminder of that later today. Okay, or later ending files. All right, so let's go to notes here, page 6. All right, so a tangent line of the function can give you an approximate value for points close to A. So I'm just going to draw something for us to have a visual here. So let's say we have a graph that's concave up, and let me just pick a random point here. Let's say there's a point 6 here, and let's say you want to create a tangent line. So let's say you find the slope of the graph, and you find the order pair, and you create a tangent line, and let's say this is what the tangent line looks like. So obviously, if I do, let's say this is f of x, and let's say this is y of x. Let's say y of x is my linear graph here. If I do y of 6 versus f of 6, I'm going to get the same y value, right? Because if it is truly tangent, then they're going to share the same order pair, and they will share the same slope between the curve and the line. Right? Now, let's say I pick a point slightly to the right of 6, and I find f of 6.1, which is the exact value on the curve, versus this point here, which is y of 6.1. Obviously, y of 6.1 is going to be an approximation. It's not going to be the exact value of the graph, but it should be pretty close because we're pretty close to our point of tangency. But which one will have the higher value? F6.1. Okay, so your tangent line will produce what we call this an under approximation. Okay, And here's the big idea is that it doesn't matter where the tangent line is on a graph that is concave up. Every tangent line that I can create, every tangent line will give me an under approximation of the actual point on the curve, just because of the way that the curve is shaped. Okay. So tangent line for a concave up graph will underestimate function value. So you can write that here, tangent line. Here, I'll just show you. So guess what a tangent line is going to do with a concave down graph? Tangent line will overestimate, because your tangent line is always going to skim the surface of the graph in a way where any remaining portion of the line is going to always sit above the graph. And I don't feel like there's any need to memorize this. If you can just draw a graph that's concave up and concave down, you should be able to quickly convince yourself whether your tangent line is going to over approximate or under approximate. Okay. All right, so before we get to number one here, I'll just write down some quick steps that you will take when you are doing linear approximation. Everybody good with this? Take this off. Okay, so linear approximation. So the name of this concept is basically describing everything that we're going to be doing. We're going to find a line, and we're going to use the line to approximate a value on the curve, and it's usually a decimal value. So your steps for linear approximation is first, you're just going to find your tangent line equation. Okay, we know how to do that. Find your order pair, find your slope, point slope form. And then the second thing is you're just going to insert, or you're just going to plug in your decimal value. And usually the decimal value will be close to your point of tangency so that you can get a more accurate approximation. We don't have to worry about how accurate the approximation is. We'll just do whatever they ask us in the problem. Okay, so that's all it is. You're just finding tangent line equation, and you're just doing one step beyond it. Whatever decimal they give you, you just insert that into the function or into the equation. Okay, so our function is concave up, and f of 4 equals 5, and f prime of 4 equals 3. So you know your graph looks like this. Right. What is the estimate for f of 3.5 using local linear approximation? Okay, that just means using linear approximation. So let's build our tangent line equation. So what's our order pair?
4, 5.
4, 5. What's our slope? 3. Yeah, point slope form, right? So I'm just going to get y by itself. Just makes it a little bit easier for this next step. So but I'm just doing some quick rearranging of tangent line equations. So we're good here, right? Sometimes we may have to build the function and find the order pair and the slope from where we have to do a little bit more work. But here they're giving us that information, so it's quick to get to that tangent line equation. Okay, everybody good so far? So we have our tangent line. So they're asking us to do an approximation of f3.8. We're not able to get the exact value because we don't have the function expression in front of us, but we do have our tangent line, and they're just asking us to use the tangent line. So we'll just plug 3.8 in for x. If this was in the non-calculator free response portion, then you can leave your answer like this. There's no need for you to clean this up, but just for our purposes right now, I'll just say, okay, that reduces to be 4.4. So we know what the curve looks. Well, we know that the graph is concave up. We don't know. We don't have the equation for that function, but we know there's a tangent line to the curve, and so this decimal value is an approximation of the actual f of 3.8. But this value, will this be an overestimate or underestimate? Under, because we know it doesn't matter where it is on this concave up graph. Any tangent line, any point that you pick that is off of the point of tangency is always going to sit below the curve, and it will underestimate. Since our function is concave up, the linear approximation will produce an under approximation. So we know that 4.4 is going to be lower than the actual f of 3.8. Okay, any questions with one? Okay, so number 2, see if you can see how far you can get. Take your function, find your order pair, find your derivative, find your slope, 2-point slope form, plug in your decimal value, decide based off of whether the graph is concave up or concave down, what conclusion can you make? Is that approximation going to be above the actual value, or will it be below? So yeah, try example 2. Okay, so number 2, we're given the function. We can find f of 1 to get the order pair. Find the derivative, go through power rule, plug 1 into the derivative to get our slope. Take our order pair and our slope, build our tangent line equation. For part B, I'm just doing some slight rearranging here. I'm just moving that 1 over just to kind of isolate that y to make it easier for me to plug in 1.1. So I know that this is not going to be the actual equation of the curve. This is just a linear approximation. So I'm inserting 1.1 into my linear equation, and I'm getting 0.9. So I know that 0.9 is some estimation of the actual f of 1.1. It should be pretty accurate because I'm pretty close to the point of tangency, but I know it's going to be a little off. And we never have to worry about how accurate is our approximation. We'll do some of that second semester with series, but right now we just have to say, okay, is it an overestimation or is it an underestimation? And then we just have to justify it by saying, okay, whether either the graph just say, oh, it's concave down. It's concave down. My linear approximation will overestimate the actual value.
Going to be given the concavity.
Yeah, I would have to tell you the graph is concave up or concave down, right? Yeah, and we haven't really talked about concavity in detail, but yeah, concave up basically has this U shape, and concave down has this upside down U shape. I'll get a lot more into it when we do our curve sketching unit. Okay, everybody good with numbers 1 and 2? Okay, it says consider the differential equation. Maybe we haven't heard that yet if you haven't taken AB Calc, but a differential equation is just a fancy word for a derivative equation. Okay, it's just some first derivative. Usually it's first derivative equation. So it just means, okay, that's my slope formula for whatever the original function is. Okay, so the problem doesn't provide you the original function. It just gives you information about it. But just know that if I want to find my slope, I can just insert into my differential equation, and in return, I'll get a number, and that number is my slope. So differential equation is just a fancy word for a derivative equation. So we should have enough information to gather what we want. Write an equation for the tangent line. So take your order pair, plug into the derivative equation to get your slope, point slope form. Then you can use that tangent line to do linear approximation. All right, any questions here? Use your derivative equation to get to your slope, point slope form. Tangent line approximation doesn't ask us for whether it's over or underestimate. This doesn't provide us enough information about concavity. So, all right, let's go to the next page. If you guys are good with that. Okay, a lot of this second page is review, so we can kind of just kind of go through it quickly. And then after this, we'll go to the extra handout that I gave you from 4.1, and we'll just try to do as many of those problems as we can. Okay, page 2. Give you guys another moment here. Okay, increasing or decreasing, we know this. To know if something is increasing, decreasing, check the sign of its derivative. Height is increasing if h prime is greater than 0. Velocity is increasing if, velocity is decreasing if v prime is less than 0. So the word increase, decrease is talking about the rate of change of whatever it's describing. Don't worry about the calculator just yet. We'll do the calculator features a little bit later. Okay, is the function already a rate of change? So let's just take this statement and see if we can put it into words what this means. So if f of x is the bunny population after x years, then f prime would represent what information?
Rate of change.
Good. Rate of change of the population per year at that particular year. Right? So our units of measure will be number of bunnies per year. At what rate is that bunny population either increasing or decreasing? Or yeah, what is the rate of change of that population? Okay, but what if f of x is already a rate? What if f of x is the rate at which a bunny population increases? Namely, if f of x is already bunnies per year, then what is f prime going to represent? Per year. How would you phrase it another way? Okay, the rate at which population is increasing or decreasing. So the way that we say, so we say rate of a rate, that doesn't quite describe it as well. So you want to say either the rate is changing or the rate is increasing, decreasing. Okay, if you want to do rate of change from a table, you just find the closest ordered pairs. And in this case, you'll just do slope. So estimate p prime of 15, estimate p prime of 20. P prime of 15, you're kind of forced into 2 order pairs, but P prime of 20, you can pick any order pairs around 20. You can choose between 10 and 20. You can choose the order pair 20, 30, or you can choose even, you can either make a case for 10 and 30. But if the value that you're estimating is exactly between 2 values, then you're forced into just using 2 order pairs. There's no, that's the best one they can use. But P prime of 20, typically I would say using these 2 order pairs or these 2 order pairs, that's usually better than using these 2, but yeah.
For the before the table, the question right before the table, isn't that saying the same thing as what the question is saying? Isn't that the same thing as f of x instead of f prime?
Well, here it says the rate. Yeah, sorry. Yeah, that phrasing is a little misleading, but they're saying it's bunnies per year. So if f of x is bunnies per year, then f prime is going to be bunnies per year squared. So
if the question were
yeah,
phrased correct, it would be how many bunnies are like produced per year or something, or how many bunnies.
yeah, if f of x is the rate at which the bunny population, yeah, the fact that it's rate increasing kind of makes it sound like a second derivative, right? It's more like f of x is or it's the rate of the bunny population change.
Oh,
Or it's the rate of change of the bunny population. How's that? I think, yeah, I think this wording does make it confusing, but they did clarify that we're talking about bunnies per year for f of x. Okay, going down to these two quick practice problems. Your store is having a 12-hour sale. The total number of shoppers who have entered the store after or T hours after the sale begins is modeled by the function E. At what rate are shoppers entering the store 5 hours after the start of the sale? So we don't have to solve this, but how would you set this up? Yeah, so E prime of 5, right? So whatever that value is, you go through power rule, plug in 5. Okay, but our units will be shoppers per hour. Okay, the function t equals f of p models the time in days for a small pond to evaporate as a function of the size p of the pond measured in liters. What are the units for f double prime of p?
liters per day squared.
Or days per liter squared?
Oh, it models the time.
Models of time. Okay, I gave you guys the 4.1 practice sheet, so if we can try some of those problems. So I handed you guys the packet, but I also gave you, I forgot to put this in the packet, so it's in a separate handout. You guys get this yesterday? Okay, so go ahead and try number 1 here. This particle is given by S of t. Find the instantaneous velocity. So find the v of t function. When it's a particle at rest, what does that mean? What's another way of saying that?
That's easier.
Yeah, velocity is 0. Acceleration is just the second derivative. And then displacement, the formula for displacements is just final position minus initial position. Oops. And it's okay to have displacement to be negative. Displacement just means how, if you get a negative, that just means you end up to the left of where you started. So VFT and AFT are relatively easy power rule process to get to each of the derivatives. To set VFT equal to 0, you do have to go through factoring. Solve for t, you get two t values. 2 times when the particle is at rest, 2 and 4 seconds. Have we talked about total distance yet? Okay, so I did that. Sorry, I did that with AB, but I haven't talked about for you guys yet. Let me just bring that up and I can review that again if we need to. So displacement is just change in position and that's it, right? Total distance requires a little bit more information because total distance means if this object is traveling back and forth, we have to make sure that we count every one of its movements as a positive value and we accumulate them as positive values. So let's do a quick example based off of this here. If you have any space, you can put that here. Let's say we want to find the total distance from p equals 3 to p equals 6. Or how about this? No, let's do 1 to 3. 1 to 3 is easier. So we still are going to gather similar information as displacement. We still want to find his position at 1, and his position at 3. But we're going to have to require a bit more information from the velocity sign line, or velocity number line. So let's say we create a velocity number line that we can use to help us track when this object is moving left and when this object is moving right. So we have a restriction here. Our domain is time is greater than or equal to 0. And we have 2 places where the object is at rest, 2 and 4. So we know that anything in between, there's movement in these intervals, right? And there's a consistent movement. So here, you're only going to move just to the left or just to the right. Here, he's only moving just to the left, just to the right. And then boron, he's just going to go in the same direction. So to test the direction of motion, we choose values in each subinterval. It doesn't matter what you choose, but typically we like to choose numbers that are as close to 0 as possible, which just makes it easier. So if I insert 1 into the velocity function, the factored form is the easiest one to collect our information. We only care about the signs, we don't care about the value. So if I test 1 here, 1 minus 2 is positive or negative. Negative, right? 1 minus 4 is negative. 2 negatives makes positive. So we know that in that time interval, 0 to 2 seconds, this object is just moving to the right. It's going to stop And let's figure out what's happening in this interval. So 3 is a test point we can choose. 3 minus 2 is
Positive,
3 minus 4 is
negative.
positive, negative, base, negative. There's a change in direction here. So he stops, he moves to the left for 2 seconds, and then let's see what happens at 5. Plug in 5,
Positive,
positive,
positive.
positive. So this kind of gives you a quick visual understanding as to how this object is moving. Okay. Now, after you do this, we don't care about these numbers anymore. If I want to find intervals of moving left or moving right, I can just pick out those intervals. Right? Moving right in this interval and this interval, moving left in this interval. Now, total distance. Total distance would be it would be the same formula as displacement if there was no change in direction. But is there a change in direction here?
Yeah.
Yes, okay. So there's a change direction at 2. So we're gonna have to figure out where he stands 2 seconds into this. Okay, so I know these numbers are a little messy here, so I'm just gonna go ahead and find those for us. But we have to find the locations at 1, 2, and 3. Okay, I know this is not a great example here because we're dealing with fractions. But just for demonstration purposes, can I just change these a bit just so I can show you? So let's say S sub 1 is at 1. Let's say S sub 2 is at 15. And let's say S sub 3 is at 5. Okay. Okay, so if we want to figure out what the total distance is, imagine yourself walking from this location to this location and then walking to this location, and you're just walking along the number line. Okay. So you're starting at 1, you're going to 15, and you're coming back to 5. Okay, so this is how you're moving. So imagine yourself, you're just walking and you're just counting your steps. And when you turn around, you're still counting your steps, so it's still a positive number in your head. So how many steps would you have taken? 14, right? 1 to 15 is 15 minus 1 is 14. Okay. And then from 15 to 5, you're still counting your steps here. How many steps have you taken from here to here? Okay. 10. So how many steps would you have taken in total? 24. So that is the speed. That's your total distance. Okay, that's how you find total distance. You find your location at your endpoints, but if there's a change in direction, you also need to find location at that point, and that way you can kind of track, okay, I walk from here to here, count the number of steps, walk from here to here, count the number of steps, just make sure that every step you take is a positive number, and then just add those together, and that's your total distance. I'll come up with a better, fuller example when we get to review, but just want to at least highlight the distinction between displacement and.
What if at like 1.5, you like turn back just for like a 1 second?
Well, it would have shown up in your velocity function,
Okay.
right? So if it doesn't show up in your velocity function, then that means there is no change in direction.
Okay.
Right? You can only change direction if he's got to stop that first. You got to stop first before you can change direction. So if it doesn't show up in your particle at rest and your sign line, then it's not going to happen. Okay. number. Let's see, okay, we're running out of time here, so maybe if we have time later on, I can come back to 4.1, but I think I just wanted to, still review some particle motion with you. Okay, there is homework from 4.2. Check your calendar, and then the bulk of our topic of this unit is going to be related rates. We'll start that on Monday. And then for unit 4, we're just going to have a quiz. We're not going to have a test. We're just going to have a quiz. And then unit 5, we'll start after next week. Okay, come get your phones.